Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine a map, but I don't want you to picture, a folded paper map in a glove box or even Google Maps.
No, this is something else entirely.
I want you to imagine a map so colossal, so incredibly detailed that it covers an entire eighth of the sky above your head. And on this map, you're not looking for roads or cities, you are looking at galaxies.
Hundreds of millions of them. It's a staggering number to even try and hold in your head.
It is. And we aren't just looking at where they are like pushpins on a corkboard. We're looking at a map that tells the story of how they got there over billions of years.
Exactly.
This is the deep dive. And today we are tackling something that has been, 25 years in the making?
At least.
As of yesterday, Thursday, January 22nd, 2026, the Dark Energy Survey, or DES collaboration, has finally released the analysis of all 6 years of their survey data.
This is it. This is the big one. I mean, we've had the year 1 results, the year 3 results, which were exciting.
Sure, they were great appetizers.
They were, but this is the full data set. This is the final word from this particular experiment.
So the mission here, it sounds so simple on paper, but I know it's just mind-bendingly complex. The mission is to understand the invisible force that makes up 70% of our universe.
Dark energy.
Dark energy.
Exactly. And to understand why this specific release is so huge, you have to look at the sheer precision.
Yeah.
This isn't just another star chart. It is the culmination of a quarter-century dream to really nail down the history of the universe's expansion.
Okay.
And these results, the constraints they provide, are twice as tight as any analysis we've done before.
Twice as tight. I want to pause on that because that really is the headline, isn't it? In physics, narrowing down those error bars is just as exciting, sometimes more exciting, than finding a whole new particle.
Oh, absolutely. Because you're effectively running out of places for alternative theories to hide.
Right.
When your constraints are loose, you can fit all sorts of wild ideas into the data. You can say, maybe gravity works backwards on Tuesdays, and if your data is fuzzy enough, you can't prove it wrong.
You can't rule it out.
You can't. But when you tighten those constraints, when you drill down into that precision, you start squeezing those other theories out of existence.
But, and I always love a good but, in a science story, there is a twist.
There's always a twist.
Yeah.
The universe, it rarely gives up its secrets easily.
So while our standard model of physics held up remarkably well against this massive data set, there is this persistent, nagging little mystery in the numbers.
Mm-hmm.
It's about how clumpy the universe actually is, and it's refusing to go away.
That is the part that has everyone, myself included, scratching their heads today. It's a subtle discrepancy. We call it the S8 tension, or the clustering gap. But in physics, subtle discrepancies. That's where the next revolution begins.
It's the loose thread on the sweater.
You pull on that, and who knows what unravels.
Okay, let's unpack all of this. Before we get to the clumpy mystery and the invisible forces, we need to set the stage. Because this story really begins about 100 years ago, doesn't it?
It does. To understand why DES is such a big deal, you have to understand what we thought the universe was doing before all this.
So rewind to the 1920s.
Right. Back then, that's really the baseline for our modern understanding of the cosmos.
Yeah.
Before that, the general idea was that the universe was static, eternal, unchanging. It was just there.
Yeah.
But then Edwin Hubble and his peers, they made this startling realization.
Galaxies are moving.
They're moving,
Yeah.
and not just moving randomly like, bees swarming out of a hive. There was a specific relationship. The farther away a galaxy is,
The faster it's moving away from us?
the faster it's receding. This is the discovery of cosmic expansion. The actual fabric of space itself is stretching, and it's carrying the galaxies along for the ride.
Okay, so the universe is getting bigger. I think most people are familiar with that concept. But for decades, there was this logical assumption that came with it, right? A prediction about what would happen next.
Yes, the logic trap, as I like to call it. And it makes perfect sense intuitively. Think about gravity. Gravity pulls things together. Mass attracts mass. So if you have a universe full of stuff stars, gas, galaxies, dark matter, all of it pulling on each other, you would naturally, logically assume that this initial expansion from the Big Bang should be slowing down.
It's like throwing a ball in the air. You give it that initial push, that's the Big Bang, but as it flies up, Earth's gravity is constantly pulling it back. It slows down.
Exactly. Everyone assumed the universe was that ball. For about 70 years, the only question was, how fast is it slowing down? Is there enough mass to stop it completely and cause a big crunch where everything collapses back in on itself?
Or does it just coast forever, slowing but never quite stopping?
Precisely. We even had a name for it, the deceleration parameter.
We were so sure it was decelerating, we named the parameter after it. That's some serious confidence.
We're very confident.
Yeah.
But then came 1998, the year everything we thought we knew just got flipped upside down.
This is the 1998 shock. I remember reading about this. For the scientific community, this must have been like, I don't know, like finding out the Earth is actually flat.
It was that level of paradigm shift, yes. You had two independent teams of cosmologists, the Supernova Cosmology Project and the High-Z Supernova Search Team, and they were both looking at the same thing.
Distant Type Ia supernovae.
Distant Type Ia supernovae.
We should probably define that because Type Ia comes up a lot in the DES papers. Why are these specific explosions so important? Why not just look at any old star?
Because a Type Ia supernova is a very special, a very standardized kind of death for a star. It happens in a binary system.
So two stars orbiting each other.
Right. And one of them is a white dwarf, the super dense core of a dead star, and it's stealing matter from its companion star.
That cosmic vampire.
Yeah, that's a great way to put it. It just siphons off gas. And it keeps doing that until it hits a very, very specific mass limit, the Chandrasekhar limit, about 1.4 times the mass of our sun. And because that mass limit is the same every single time, the explosion has roughly the same intrinsic brightness every single time.
So it's a standard candle.
It is the perfect standard candle. Think of it like a specific brand of 60-watt light bulb. If you see that bulb right in front of your face, it's blinding. If you see it a mile away, it's just a dim point of light.
But since you know it's a 60-watt bulb, you can calculate exactly how far away it is just by how dim it looks.
Exactly. These supernovae are our cosmic light bulbs. They let us measure vast distances across the universe.
So these two teams, they used these cosmic light bulbs to measure the distance to far-off galaxies. And what they found was not what they expected.
Not at all. They found the supernovae were dimmer than they should have been if the universe was slowing down.
Dimmer meant farther away.
Dimmer meant they were farther away than all our calculations predicted. The only way they could be true is if the expansion wasn't slowing down.
It's accelerating.
It's accelerating.
I always love the car analogy for this. It's like you're driving down the highway, you take your foot off the gas to coast, and you expect the car to slow down.
Right, because of friction and wind resistance.
But instead, without you touching anything, the car suddenly floors it and starts speeding up.
And you have no idea who is pressing the pedal. That is exactly the situation we found ourselves in 1998. And to explain this acceleration, physicists realized there must be some form of energy filling empty space, pushing everything apart.
And since we didn't know what it was,
we gave it a placeholder name, dark energy.
And it's not just some tiny rounding error, right? It's not a 1% effect you have to squint to see.
No, far from it. Our current estimates suggest dark energy makes up roughly 70% of the mass energy density of the universe.
7.
0.
70% dark matter, the invisible stuff holding galaxies together, that's another 25%. The stuff we're actually made of, atoms, stars, planets, you, me, this conversation.
All of it.
It's barely 5%.
That is just, it's humbling. We are the rounding error. We're the debris.
We are the foam on the cosmic ocean. And yet, despite being 70% of reality, we know almost nothing about it. Is it constant? Does it change over time? Is it a property of space itself? This is what the Dark Energy Survey was built to find out.
Okay, so let's talk about the tool. Because you don't just go out to the backyard with a pair of binoculars to find dark energy. You need the DECAM.
The Dark Energy Camera. It is a beast of a machine. Truly one of the most advanced instruments ever pointed at the sky.
I was looking at the specs on this thing. It's a 570 megapixel camera. I mean, my phone is a decent camera, maybe 48 megapixels if I'm lucky. 570 is just, it's absurd.
It has to be. It was fabricated by the U.S. Department of Energy for this specific purpose. It uses 62 separate charge-coupled devices, CCDs, and they're all specifically designed to be super sensitive to red light. Why red light specifically?
Because of redshift. As the universe expands, the light from distant galaxies gets stretched out during its journey to us.
The light waves get longer.
Exactly. They shift towards the red end of the spectrum. So if you're looking at galaxies that are billions of light years away, their light is going to be very, very red. The camera needs to be able to see that faint, stretched out light.
And where did they put this thing?
It's mounted on the Victor M. Blanco 4-meter telescope, which is at the Cerro Tololo Inter-American Observatory in Chile.
High up in the Andes? Why Chile? Why not, I don't know, Arizona or Hawaii?
The Andes offer some of the most stable atmospheric conditions on the planet. You're high up, so the air is thin. It's incredibly dry, so there's almost no water vapor to distort the light. And it's super remote, so there is zero light pollution. It is the perfect place on Earth for staring into the deep dark.
And the scope of what they did with this camera is just immense. We're talking about data collected over 758 nights.
Between 2013 and 2019, that's 6 years of just staring. And in that time, they recorded information from 669 million galaxies.
I can't even conceptualize that number. 669 million galaxies. And each one of those has billions of stars. And we're looking at objects that are billions of light years away.
It creates a volume of data that is. It's hard to comprehend. We're talking petabytes of information.
Yeah.
And this wasn't a small team either.
No.
This is a huge international collaboration. Over 400 astrophysicists from 35 institutions across 7 countries.
It's a global effort to solve a universal mystery. So, okay, they have the camera, they have the data, but how do you actually weigh something invisible like dark energy? You can't see it directly.
No, you can't. You can only see its effects on the stuff you can see.
Uh-huh.
And this brings us to the methodology, which is what makes this year's release so special. For the first time, they've combined all 4 of the probes or methods of measurement that were originally proposed when DES was just an idea 25 years ago.
The big 4.
The big 4. So briefly, you have baryon acoustic oscillations, or BAO. That uses the scale of sound waves from the early universe as a sort of standard ruler.
Like a cosmic yardstick frozen into the sky from the beginning of time.
That's a great description. Then we have the Type A supernovae, which we talked about, the standard candles. Right. Then we have galaxy clusters. You literally just count how many massive clusters exist at different points in history.
And if gravity is winning, you get more clusters. If dark energy is winning, you get fewer.
Exactly. And finally, the heavy hitter for this analysis, weak gravitational lensing.
Okay, I want to double-click on weak lensing. Because reading through the reports, it really seems like this is the bread and butter of the DES analysis. This is where the magic happens.
It is absolutely fundamental. It's arguably the most powerful tool we have for mapping dark matter, which in turn tells us about dark energy.
So explain this to us. What is weak lensing? It sounds like a vision problem.
It does, doesn't it? But it's actually a direct consequence of Einstein's general relativity. Einstein told us that mass bends space. It curves the very fabric of the universe. So imagine light traveling from a very, very distant galaxy towards us here on Earth.
Okay.
On its long journey here, that light has to pass by massive objects. It could be clusters of other galaxies, huge clouds of invisible dark matter.
And the gravity from those objects bends the path of the light, right? Like a glass lens bends light to soak.
Exactly. Okay. So the gravity acts like a lens. Now, sometimes this lensing is strong. You see these weird, beautiful arcs or rings or multiple images of the same galaxy. That's spectacular, but it's rare. Weak lensing is much, much more subtle. It's a tiny distortion in the shape of the background galaxy.
So it squishes it a little bit.
A tiny amount. We're talking about a distortion of roughly 1%.
Wait, 1%? How can you possibly tell? I mean, galaxies are already kind of blobs. Some are spirals, some are elliptical, some are just messy, irregular shapes. How do you know if a galaxy is distorted by 1% or if it's just naturally shaped like that?
That is the genius of it. You can't tell for a single galaxy. It's totally impossible.
Yeah, what's the trick?
The trick is statistics. If I showed you just one galaxy, you couldn't tell me if it was lensed or just naturally oval-shaped. But if you look at millions of galaxies, patterns emerge. In a random universe, galaxies should be oriented randomly. Some pointing up, some down, some left, some right. Just a total jumble.
So the average orientation should be 0, no preference.
Precisely. But if you look at a certain patch of sky and you see that the galaxies there are all slightly aligned or distorted in a similar way, a phenomenon we call cosmic shear, that tells you something.
It tells you there's a massive amount of matter in front of them.
Yes. A huge lens distorting the wallpaper in the universe behind it. And that's how we map dark matter. If the light is bent, there must be mass there, even if we can't see the mass itself. We can create a 3D map of the invisible scaffolding of the universe, based purely on how it warps our view of the stuff behind it.
The source material mentioned the bullet cluster as a famous example of this in action.
The bullet cluster is the classic smoking gun. It's 2 galaxy clusters that collided, a massive cosmic car crash about 3.7 billion light years away. When we look at it with weak lensing, we can see where all the mass is.
And it wasn't where the normal matter was?
Not at all. The normal matter, the hot gas, it crashed and got stuck in the middle due to friction. But the dark matter, the bulk of the mass, it just passed right through itself like a ghost. It proved that dark matter is real, and it's separate from the stuff we're made of. It doesn't interact except through gravity.
That is just wild. So DES is doing this, but on a massive scale.
On the scale of the entire survey.
Yeah.
They are measuring the probability of any two galaxies being a certain distance apart and how they are distorted. By doing this, they can reconstruct the distribution of matter over 6 billion years of cosmic history.
So they're building a 3D movie of the universe's structure. They can see how clumpy the dark matter was 6 billion years ago, 5 billion years ago, 4 billion.
Precisely. And that finally tells us about dark energy. Because remember, this is a war. It's a cosmic tug of war. Dark energy is pushing things apart, trying to smooth everything out. Gravity is pulling things together, trying to make them clump up.
Yeah.
By measuring the clumpiness over time, we can see which force was winning at different eras.
Okay, so we have the arena set. Gravity versus dark energy. The data is in 669 million galaxies analyzed. What's the verdict?
Well, it comes down to a battle of the models. In one corner, you have the heavyweight champion, lambda CDM.
The standard model of cosmology.
The vanilla option, yeah. In this model, lambda stands for the cosmological constant. This is an idea Einstein originally had, then threw away, then we had to bring back. It says that dark energy is a constant force. It doesn't change. It's just a property of empty space.
So every cubic meter of space has a set amount of this energy.
Exactly. If you make more space, you get more energy. It's simple, it's elegant, and honestly, it's a little boring.
And in the challenger's corner,
we have a model we call WCDM. In this model, dark energy isn't necessarily constant. It has this parameter, we just call it W, that describes it's called its behavior. If W is exactly -1, it's constant. That's lambda.
Okay.
But if W is different from -1, or if it changes over time, then dark energy evolves. It could be getting stronger, which might lead to a big rip where atoms eventually get torn apart, or it could be getting weaker.
So after all that, who won?
The standard model, lambda CDM.
Einstein is still right.
Einstein is still right. The analysis from all the papers submitted to Physical Review D shows that the data is perfectly consistent with a constant dark energy density. The value of W they found is effectively -1, well within the error bars.
Now, I can hear some listeners groaning, "Oh man, the standard model won. That's so boring. We want new physics."
I know. We all want warp drives and new dimensions. But you have to understand the triumph here. The real victory is in the precision. The report says these results are consistent with the standard model, but the constraints are twice as tight as previous analyses.
Meaning that window of error has been cut in half.
Drastically. It means that if there is some weird, evolving dark energy out there, it has to be hiding in a very, very tiny sliver of possibility. We are squeezing the space where those alternative theories can live. The data fits the evolving model, sure, but not any better than the simple one. So Occam's razor applies.
You go with the simpler explanation.
You go with the simpler explanation.
So dark energy appears to be constant. But, and here comes that but we teased at the top of the show, there is something in the data that doesn't quite fit.
The clustering gap, or as we call it, the S8 tension.
This is the plot twist. Tell us about this gap.
Okay, so we have two different ways to figure out how clumpy the universe should be today. Method 1. We look at the very beginning of the universe.
The baby picture.
The baby picture, exactly. The cosmic microwave background, or CMB. This is the afterglow of the Big Bang, measured with incredible precision by the Planck satellite. We can measure how clumpy things were back then, these tiny fluctuations in density. Then we use our standard model, lambda CDM, to fast forward 13.8 billion years and predict how clumpy the universe should be now.
Okay, so that's the prediction. Based on the baby picture, we predict what the adult should look like.
Right. Based on how you looked at age 1 and knowing how humans grow, you should be 6'2". That's the prediction. Now, method 2. We use the dark energy survey to actually go out and measure how clumpy the universe is right now using weak lensing.
We take a photo of the adult.
We take a photo of the adult.
And do they match?
They don't. Not quite. The universe we see today, the adult photo, is slightly smoother than the prediction says it should be. It's less clumpy. The parameter we use to measure this, S8, comes in lower in the lensing data from DES than it does in the prediction from the CMB.
Wait, so the math says gravity should have pulled things into tighter, denser clumps by now, but the actual picture says, nope, it's a little more spread out.
That's it, exactly. It's like predicting someone will be 6'2", but when you measure them, they're 5'11". It's close,
Yeah.
but it's definitely not the number we expected.
Is it a mistake? A systematic error? Did someone forget to carry a 1 somewhere?
That is the multi-billion-dollar question. In the previous analyses, DES year 1, year 3, we saw a hint of this. But people thought, okay, maybe it's just noise, a statistical fluke. Maybe we didn't account for galactic dust perfectly. But now we have the full 6-year data set, the most precise map ever made. And the gap didn't go away. In fact, it widened slightly.
It's stubborn.
It is very persistent. And it's showing up in other weak lensing surveys too, like the kilo-degree survey. Now, to be scientifically responsible here, the discrepancy is roughly 2.5 to 3 sigma.
Translate that from statistics speak for us. What does that mean?
It means there's roughly a 1 in 100 or 1 in a few hundred chance that this is just bad luck, a random fluctuation. It's not yet at the 5 sigma level, which is the gold standard in physics for claiming a discovery. So we can't definitively say the standard model is broken.
But it's enough to make people sweat a little.
It's enough to keep cosmologists up at night. Because if this gap is real, if the universe really is smoother than our physics predicts it should be, it implies that something fundamental is missing from our understanding.
What could it be? I mean, if it's not a mistake, what kind of physics could cause the universe to resist clumping up?
That's the fun part. This is where the theorists get to play. It could be, well, it could be that gravity behaves differently on these massive scales than Einstein predicted. Maybe gravity gets a little weaker over huge distances. It could be that dark energy does interact with dark matter in some way we haven't thought of. Maybe it gives dark matter a little push, preventing it from clumping as tightly. Or maybe there's a new type of particle, like a new kind of neutrino, that's just zooming around and smoothing things out like a cosmic iron.
So this is the potential aha moment. The standard model survived the main test, the expansion rate, but this little gap, this is the loose thread. You pull on it, the whole thing might just unravel.
That is the most exciting thread to pull on in all of cosmology right now. We confirm the basics, but in doing so, we might have found a crack in the foundation.
So speaking of the future, the Dark Energy Survey has finished its data collection. The survey is done. What happens next?
Well, the baton is being passed. DES paved the way. It proved that these techniques, like weak lensing reconstruction on a massive scale, actually work. It was the training ground. Now we are leveling up in a big way.
Enter the Vera C. Rubin Observatory.
Yes. The NSF DOE Vera C. Rubin Observatory. It's being built in Chile right now, not too far from the Blanco telescope, actually. And it's going to conduct what's called the Legacy Survey of Space and Time, or LSST.
I love that name. Legacy Survey of Space and Time. It sounds so epic.
It is appropriately epic. Just think about the scale difference. DES looked at 669 million galaxies over an eighth of the sky. Impressive, right?
Extremely.
The Rubin Observatory is going to catalog about 20 billion galaxies.
Whoa, from 600 million to 20 billion.
And it will cover the entire southern hemisphere sky. It's not even a static map. It's going to scan the whole sky every few nights. It will essentially make a 10-year time-lapse movie of the universe.
That's an exponential leap.
It's a generational leap. It'll take the constraints we just got from DES and tighten them even further. If that clustering gap is real, Rubin will find it. It will make it undeniable. It will turn that 2.5 sigma hint into a 5 sigma gold standard discovery.
Or it will prove it was just noise all along.
Or it will prove it was just noise and we can all go back to sleep. But either way, we'll know. It's like DES built the foundation and now Rubin is going to build the skyscraper on top of it.
It really feels like we're entering a golden age of this kind of work. You know, when we started this, we talked about a map. And what's amazing is that for most of human history, mapping the universe meant drawing constellations, connecting dots to make pictures of bears and hunters.
We were just projecting our own stories onto the stars, trying to make sense of the chaos by drawing familiar lines.
Right. And now we are mapping the invisible scaffolding of reality itself. We're weighing the dark matter that holds galaxies together and measuring the dark energy that's ripping them apart. We are not just drawing bears anymore. We are drawing the forces that created the universe the bears live in.
And we are doing it with a level of precision that would have just seemed like magic a century ago. Imagine telling Hubble in 1929 that one day we'd be measuring the 1% shape distortion of 600 million galaxies to weigh the vacuum of space. He would have thought you were insane.
It really is an incredible human achievement. 400 people working for over a decade just to verify a theory proposed before some of them were even born.
And in the process, to find that one little loose thread that might lead to something entirely new, that's what science is. It's not about having all the answers. It's about finding the next better question.
So, as we wrap up this deep dive, here's the takeaway. We looked at an eighth of the sky. We analyzed hundreds of millions of galaxies. And we confirmed that, yes, the universe is expanding under the influence of a constant dark energy.
Einstein is still the boss.
But the universe is smoother than it should be. And that is the thought I want to leave you with today. The universe is smoother than our math predicts, based on how it started. So if the beginning and the present don't quite match up, what happened in the middle? Is gravity changing its rules when we aren't looking? Or is there a piece of the puzzle floating right in front of our faces that we just haven't learned how to see yet?
The standard model survived this test, but that little gap, that might just be the door to a whole new physics.
Thanks for listening to The Deep Dive. Keep looking up.